We are solving a system using a method that we call y1 equals y2. And I've also heard this method called the equal values method. This is our third way of solving a system. Our first way was solving a system by graphing, and we also solved a system using tables. And this is our first algebraic approach to solving a system, meaning we're going to write and solve an equation in order to find the solution. Let's go ahead and look back at our previous toolkit where we solved using tables and use these tables to remind ourselves that the solution to the system is the x and y that exist on both or for both equations. So for most values of x, the two y values are different given the two different equations. So when x is 1, 4x minus 9 is different than x minus 3. But only at the solution, given the x, the two y's are the same. We can use that fact to acknowledge that at the solution, the two y values are the same. Not always, not most of the time. For most values of x, these two y's will be different. But at the solution, the x and the y will be the same. So since the y's are the same, and since y equals 2x minus 3 for the first equation and y equals negative x plus 12 for the second equation, we can go ahead and set these two equations equal to each other. Or more precisely, we can set the right-hand side expression of both equations equal to each other. 2x minus 3 equals negative x plus 12. Again, this is possible because at the solution, the y values will be the same. I now have a pretty basic equation that I know how to solve. There's only one variable, so I can solve this now. Add x to both sides, I get 3x minus 3 equals 12. Next inverse operation, I add 3, and I have 3x equals 15. Divide by 3, I get x equals 5. So I'm going to skip ahead right here to acknowledge that I know half of my solution. A really common mistake is to just stop here. We're used to solving an equation and stopping when we have the solution to that equation and just saying, hey, I'm done, x equals 5. We're not just solving an equation here, though. We're solving a system, so our solution will always be an ordered pair. The x value of my ordered pair is 5. I now need to find the second half of my solution, the y value. So I'm going to do that by plugging x back into either of the equations, my choice. I usually just use the first one because why not? Y equals 2 times 5 minus 3, which is 10 minus 3, which is 7. So that gives me the second half of my solution. So my solution is the ordered pair 5, 7. In my directions, I say to check my solution using the other equation. As long as I plugged x in and did my computations correctly, we would assume that 5, 7 is a solution to this first equation that I used. I can check that mentally. Does 7 equal 2 times 5 minus 3? Does 7 equal 10 minus 3? Yep, 7 equals 7. You can always check with both equations, but more importantly is to check using the other equation that I haven't already used. So does 7 equal negative, plug in the 5 for the x. I didn't really need parentheses there, but it doesn't hurt. Does 7 equal negative 5 plus 12? Does 7 equal 7? Yes. So that shows me that I didn't make any computational mistakes. 5, 7, x equal to 5, y equal to 7 is a solution to this equation. It's a solution to this equation, and therefore it is a solution or the solution to this system. For this method, I'm always going to end up with x first. So it's not typically a big error where you switch the x and the y, but just always be careful that you write your ordered pair with x first and then y. And of course, never forget to write your solution as the entire ordered pair.